It's my pleasure to introduce our first keynote speaker today, Dr. Rob Stephen. Rob is the president of global organisation CIGRE. Rob was born in Johannesburg, South Africa. He graduated from the University of Witwatersrand in 1979 with a BSc Electrical Engineering degree. He holds both MSc, MBA degrees as well as a PhD in overhead line design. He joined electrical utility Eskom in 1980 and is currently the Master Specialist in their technology group, responsible for distribution and transmission technologies of all voltages covering both AC and DC, and was responsible for the smart grid strategy for Eskom. He is past chairman of CIGRE SCB2 on overhead lines and has held positions in CIGRE of special reporter and working group chairman, and has authored over 100 technical papers. He was elected international president of CIGRE in 2016 and is also a fellow of the South African Institute of Electrical Engineers, SAIEE, and was elected honorary vice president in 2005. He received the SAIEE President's Award in 2016. So welcome, Rob. We look forward to your keynote presentation.
Good morning, ladies and gentlemen. I'm going to cover quite a lot of work that has been done by the CIGRE Technical Council, and this is a group of the 16 study committees, those of you that are familiar with CIGRE. This is a global organization, 90 countries, and we've got about 59 national committees. So we run about 230 work groups concurrently at any one time, with about 3,000 international volunteer experts working on these problems. So it's really a good problem-solving organization, and one of the areas they look at is really future grid and what is happening into the future and what technologies, changes and so on that we should look to. I'll also get, rather than dealing with high level, I'll delve into two of the areas in a little bit of technical detail, which I hope you'll find interesting. So what are the challenges? And these are really the as been mentioned before, policies on lower carbon, integration of renewables and distributed generation into the grids, a big increase on customer participation and in various modes, and depending on different market designs. And then progress in technology, including ICT, and there you're seeing a lot of merger between IT and OT technologies, which was sort of unheard of in the past. Then, of course, we've still got the existing grid. So the end of life, the life extension, and grid renewal are really focused sort of challenges at the moment. And then we've got in Africa and Asia really large areas where there is just no electricity supply at all. So how do we actually connect to these areas? What are the challenges relating to connecting, giving electricity into remote areas, and what technologies do we use for that? And then, of course, market design, which actually now starts affecting your entire operation of the network and so on, and then your environmental compliance. So, purpose of the power system: high reliability, security of supply, most economic and best environmental protection. And of course, none of those really go in sync with each other. They're always competing. And this is one of the big challenges, of course, being an engineer, to try and balance all of these together. There was a study done on what grid models are going to go forward. And if you remember, some years back, when renewables were started, they said, well, you don't need transmission lines ever again, because you're going to have everything's going to be just on your roof, and you're going to be totally off grid. And what they found was virtually exactly the opposite, because when you get grid-scale renewable generation, it's normally placed in areas where there's no lines, there's no load, there's nothing. So you then have to have lines coming from there into the load centers. So they actually realize that we're still going to need large networks with bulk transmission, but there's also this clusters of small distribution networks, the microgrids. And the microgrids can be standalone, they can be part of the grid. And so and a combination of various between how much integration or not. So the finding was that you can't ignore one or the other. You actually have to look at a mix of these two models of grids. So this is really your past system. And in fact, most of the world is still operating in this mode to a large extent. But this is really where your evolution comes in, where you've got generation at any point, at any voltage, and power flow in any direction at any time, at any voltage. So now you can have MV feeding back through to your transmission network, and this has been found in Germany with a large rooftop PV program, that you're getting back feeds through the transmission transformer. So now all your tappings, whereas a transformer tap for transmission was normally going only in one direction, now you have to see, have you got voltage problems going in the other direction, the power flows in the other direction. It was never really planned for that. What they've identified in CIGRE is 10 areas which need to be focused on simultaneously. And each of these areas really is integrated and one affects the other. So your active distribution networks really is what you might term your smart grid. But that leads to, as well, with your smart meters, massive exchange of information, your big data management. And often big data is actually worse than small data because it's just too much and you actually just make absolutely no use of any of it. And the importance of how to actually manage the data, who owns it, who uses it, and what analytics you want to get out of it is extremely important to decide up front. Then your integration of HVDC and power electronics with the cost of the inverters coming down, your voltage source converters, your HVDC up to 2000 MVA now, voltage source converters, they've now got a DC breaker as well, they claim, so you can get DC grids, and of course MV and LV DC, which we're looking at. Then installation of storage, and then the one thing I'll touch a little bit more on is operation and control, and then your protection, of course, and that's your varying fault levels and the need now for wide area protection systems and automated changes of relay settings. And then new concepts in planning. Planning used to be fairly complex, now it's ridiculously stochastic, so it's almost you don't know where the load is varying and it changes from a load to a generator. And then, of course, in managing that, you need new tools. And then increased use of existing infrastructure, and I'll cover a little bit more on that point as well. And then stakeholder awareness, the consumer now becoming a lot more involved in what you do and how you manage your network. And there's a panel after lunch which will deal with quite a lot of these points in more detail. Just looking at the new key elements that are coming in is continental and intercontinental connections, deployment of variable sources, your energy storage at all voltage levels, residential and business generation, and of course your increase in new consumers, e-mobility, heat pumps, and so on. And really, as you know, your inverter-based resources, and these, while we call them inverter-based and not renewables, hydro is renewable, but it's not inverter-based. So you have a totally different problem with your inverter-based resources that you would have with your synchronous renewable resources. But you can see the increase there just in China, going up to, within the next couple of years, over 150 gigawatt of PV. So it's a really, really huge amount of growing resources. At the moment, about 98% of storage is pump storage. It's not batteries at all. However, if you look at PV combined with storage, you can expect around 21 gigawatts coming online in the next sort of 7 years. Just to get a little bit onto your system operations and control, as when you start getting your inverter-based resources, there's quite a lot of challenges that you have. and these are power balancing, congestion management, active reactive reserve, and risk management and probabilistic approaches which are needed to actually manage your operations. And I think in New Zealand you're fairly blessed in having the large hydro, whereas in many other countries it's really an old coal-based system, and most of the generators around the world are in fact still coal generators. And they might say they're phasing them out or they're doing something, but they're actually still running a lot of, there's an enormous amount of coal generation that is still going on. These are really the brochures that CIGRE have managed to produce. We produce about 40 a year, but most of these that are sort of in numbers that are about 500 and down are free of charge off the website. So you can see that they deal with quite a lot of different topics relating to this. Just to have a look at this is quite an interesting table that was produced by EPRI, Electric Power Research Institute in the US. And it indicates on the left your synchronous interconnected, and on the right-hand side is your inverter-based, so that your grid-scaled wind PV, distributed PV, and distributed battery storage, and in the last columns is demand response. So on the left, what you really want when you operate your network is you want the green, and you want at least sort of a score of at least 4. So you can see the 4 there is the green with a tiny bit of yellow, and you need that right across your network for all of those columns on the left. So you can see the only one that really gives that is hydro. And if you go a little bit across to the inverter-based, you'll see that doesn't have much green at all. So the problem on the inverter-based is that if you're trying to run your networks up to very high percentage penetration on inverter-based resources, you're going to have to find somewhere to make those dots green. And to do that, you're going to have to do something about it, which means you're going to either have to have gas or coal or hydro available. So the inverter-based benefit, of course, has got zero fuel cost. And the one on the left, of course, is that it's not really geared to provide ancillary services at the rate that you want from your inverter-based resources. And this is where you get your duck curve coming in. And looking at California, they're running at about, they reckon in the next few years, I'll be looking at 13,000 megawatt duck curve per hour coming through that you require on a ramp rate. Now you try and do that on a coal station, you just can't do it. The other problem is coal doesn't like running really light load, because your boilers start becoming unstable. So what you have to do is really start looking at how do you change your furnaces, your boilers, your control systems to enable them to run really light loads, and then to increase their ramp rates. The other big problem is your frequency control, and the big thing there is your inertial response. Basically, what happens with synchronous generators, if you've got a fault, the generators are just so large that it'll just keep turning and ride through the fault, especially in the few first milliseconds. If you take all your synchronous generators off the grid, and you've only got inverter-based, then you've got a real big problem. And that was a bit of the problem that happened in South Australia, where they actually had the blackout there. That was the rate of change of frequency was just far too high for the under-frequency load shedding schemes to actually operate, and they actually resulted in a blackout. So what you need to really understand is how much inertia you need on the system and where you're going to get it from, and you must make sure that you keep that going. And the trick is, of course, to try and keep the inertial response going without curtailing your inverter-based resources too much. So this is really the trick coming in. There's been a lot of work now looking at synthetic inertia and so on, but the synthetic inertia still has limitations, and that's on from your DC and from your inverters with batteries. You can also see there that nuclear doesn't solve all your problems. So your nuclear is really good for your inertia, but it's not good on your black start, ramping, and spinning reserves. This is a concept which is now raised by, because of this problem, by China State Grid, and they've set up a group called the Global Energy Interconnector. And they've now done some really serious studies to look at if they put terawatt-sized stations, renewable stations around the world, the argument is somewhere around the world the wind will be blowing and the sun will be shining. So if you can get the power to come from one side to the other, you could most probably have a renewable based with enough inertia from your hydros to supply. And this is a map from the Federal Institute of Technology. And it's actually, if you look at it, first of all, you think, well, this is daft, but it's actually starting to gain some traction, and CIGRE are doing some work to see exactly how we can actually, if this is possible and how it could actually work. They're looking at about 4,500 kilometer lines, 10 gigawatt transformation, and they're looking at AC and DC coming in with a few thousand, with really large stations. But if you look at China, they're putting in 40 gigawatt of generation per year. So, this is perhaps nothing too much for them anyway. Looking at that available technology, we've now got UHV up to 1200 kV AC, and they're starting to build 1100 kV DC. The big thing is submarine cables can now go to 3,000 meters, which means that you can now use cables to get across very deep chasms between continents. Digital substations, of course, compact GIS to put really big wind turbines on, and they're developing a 20 megawatt wind turbine now, 250 meter diameter. And then, of course, hybrid lines, AC to DC. This is really the challenge if you're looking at sustainable electricity for all. You can see we've got sort of a house, and you'll see there's a few of the challenges are there's really low density, so you can get down to around 30 houses per square kilometre. Very low demand, 0.4 kVA. There's no address, so you can't send a bill to them. And the other problem is that your house can't support a connection. You bring your connection, it pulls the wall down. The house may move, and you often go there and find that that's all that's left of the house is your meter. Everything else is gone. There's not even the house there. So these are the challenges that you actually have to face. And you put a microgrid there, you're still going to have to run 900 meter LV lines, try and get to these houses. So that's quite a challenge. Just to then get on to something a little bit more technical now. This is the item number 9. And there's been, because of the power flow and the churn, there's a need to really look at how to operate the existing lines and replacing old conductors by high temperature conductors. You can retension existing conductors, you upgrade the voltage level, real-time thermal rate monitoring, etc. And I'll just cover use of high HTLS conductors, a high temperature low sag, and then also the real-time monitoring. Conversion of AC to DC, there's a brochure on that from CIGRE. This is really the guides if you want to look at it. That brochure at the bottom, 244, is going to be updated soon. But it's quite a good brochure if you want to get into changing conductors on transmission lines. So just having a look at this, really the thermal rating of a line, if you need a certain amount of power, say 1,000 amps, you can do it in many different ways on a transmission line. You could use a 800 millimeter conductor, and you can run that at about 70 degrees C, or you could use a 400 millimeter conductor, you could run it at 100 degrees C, or you could use a 200 millimeter conductor, and you can run it at 200 degrees C. So now the big thing is, say you want to operate, and you've got a line at the moment which has got a 400 mil conductor, but you need to increase the current down that without changing your right-of-way and without changing the towers. And you need to increase the current on that, say, by 2 to 3 times. How do you actually go around doing that? And that's where your high-temperature, low-sag conductors come in. Now, there's many, many types, and I don't know if you're from the utility, you've most probably been visited by one or two of the manufacturers to tell you that their conductor's the best thing since sliced bread, and it's the only one that you should really use. Well, it might be the case, but you need to know what you're doing when you actually start selecting a particular conductor for your particular application. And that's what I want to really just cover a little bit of. For a start, you can look at the different kinds of materials. And there's hard drawn, which is our normal aluminium that we normally put up. Then you get a thermal resistant, which is a TEL, and then you can get a super thermal resistant, which goes up to 210 degrees, which is a Z-TEL. And these are just a few examples. There's about 10 different types of these types of alloys, all going up to various temperatures. And the interesting one is also fully annealed aluminium, which came out in the 60s, which goes up to 200 degrees C. So now, depending on what kind of material you want to put on the outside of the conductor, what are you going to put on the inside? And then you've got galvanized steel, extra high strength, aluminium clad steels, mesh metal, which is used quite extensively because it's actually very corrosive protection, and it goes up to high temperatures. And then your galvanized invar meaning invariable, so it doesn't vary with temperature, so your sag doesn't vary with temperature. And then, of course, there's a range of carbon matrix materials and polymers and carbon core conductors. So these are the types of things. You can also choose different strandings. You can have a trapezoidal strand, a round strand, there's a Z strand, and you can see there's a polymer carbon composite core on the lower left. Now there's also single cores, that's a single strand core, or a multiple strand core. So there's a number of these that you can choose from. And then you can see on the top right that there's a gapped conductor. And you might well, why you put a gap in between the core and the aluminium. So there's a lot of these that you can choose from, and they all vary in price, and it depends on how you want to apply them. So looking at the selection, say you've got a line, and your original line was sagged to the dotted line, but you've got a 2 meter, the surveyors at the time allowed a 2 meter buffer. So you've got a maximum sag there to about 13.5 meters. And say you now need to go from your 50 degrees C or 75 degrees C, which is a little dotted line, across to your, say, 150 to 200 degrees C. What conductor do you actually choose? And the important thing here is to really look at your knee points. And you can see that the blue line has a very high knee point, and that's your... even though the core is invar core, so as soon as it hits a knee point, when we talk about knee point, it means all the load that's on the aluminium goes into the core. So now the core is supporting your entire conductor. The aluminium's not supporting it either, at all. And the earlier you have that, the flatter the temperature sag curve becomes. So depending on what you really need and what temperature you need to go to, you might then decide on which conductor to use. And interestingly, you can see there that the blue line, in fact, is most probably not going to be suitable for you because it hits your maximum sag at around 110 degrees C. Even though that conductor can go up to 200 degrees C, it's not going to help you. But the ACSS, which is aluminium conductor steel supported, has a very low knee point and can actually go a lot higher before it actually reaches sag. It can go to 210 degrees. And then, of course, you're gapped, and this is why you have the gap, so that you've got a very low knee point. It can actually carry on right up to over 200. It's just above your original sag anyway. So you can then, with the same conductor diameter, put that particular conductor up. You don't need to change your towers. You don't need to change really anything else. And you can then increase your rating of the line quite substantially. And this is a case in Spain where they needed to go from 370 amps to 1500 amps on a particular line. And these are all the different types of conductors. The black is an ACSR, their normal one. The blue is the GTZ, which is a gapped. And then you can see the red is an ACCR, which is a carbon matrix conductor. Your ACCC is a carbon cord conductor, and your ACSS is the aluminium conductor, steel supported. And they eventually chose a GZ. Mainly it was availability reasons and cost reasons. This is a very complicated conductor, so you normally only can do it from strain to strain. You can't put a mid-span joint in this thing. But on ACSS you can. You can put, and on the polymers you can put mid-span joints. So you need to be careful about that as well. But there's an example where you can go up about 5 times without really changing much on your particular conductor, particular tower configuration. I'd now like to touch really briefly onto real-time monitoring. If you've got a line and you need to actually find out how you can actually run this line, normally the rating of the line is determined by static considerations, so wind speed, solar radiation, wind direction, and so on. But you can, especially on a day like today, most probably get a lot more out of your line because it's running cold, because you got wind and you've got rain, so it's really been cooled. So the real-time rating is a function of the position of conductor in space. And so really what we're doing is we're monitoring where this particular conductor is in space at any one time. We're then using weather data and algorithms to actually say, well, if it's at that space, now how much current can I push down the line in the next hour to get it to the design or temperature? And that's really where you use your real-time monitoring. These are the measurement devices, and there are many of them. One is an angle, the other one looks at a target just to determine where it is. There's different ways of determining the actual effective wind speed and how you then determine the rating going into the future. And this is really what the operator can see. So you can see in a particular short time, you can get a huge amount of current down the line, and then over time, that amount of current that you can push down the line obviously drops. So because your conductor then increases, and your uncertainty of the weather also increases. So really this is what they have found, and this is a 2009 a twin bundle. Looking at 2,000 amps. The green is the maximum allowed, and the blue is the actual current that was down the line. So you could see in that particular case, if necessary, you could have in fact increased your current down the line above that, above that red line. The red line is your normal rating of the line. So operators normally keep your rating, the line, quite below the rating, obviously more conservative, and because it doesn't make it economic sense to run it right up to the rating of the line. But if necessary, in this case, you could have actually increased it quite a lot above the rating without increasing your temperature above the design temperature. Looking at actual case studies, what they found in CIGRE in Brazil, a delay in construction, delay in strengthening of a 138 kV line, and renewable generation. One of the nice things about renewable generation is that if you've got fairly big wind farms, although you don't have the same profile at the wind speed at the wind generator is not the same as on your line. But generally, if you've got a really high wind speed at the wind generator, your line wind speed is normally above 1 meter per second or 1.5. So you may be able to, using real-time monitoring, increase your line rating, and you don't have to curtail the particular generation from the wind farm. Also, if you design with perhaps a high temperature conductor, you can get a very high thermal rating on that particular line at a fairly low cost. So AEP in the US, they can increase capacity required for wind generation. That's an example. And then KCPL, a 16% increase in line ratings for 167 hours. This is a finding from AEP. The black line is really your rating, so that's what they would operate at. The blue line is the minimum. Really, that is a minimum rating based on the weather that they had. So you can see there the additional capacities at green bar going from the black line to the blue line, and the green is the average. So even if you take the minimum, you still get quite a bit of increase. But just beware, if your line temperatures are fairly low, around about 50 degrees C, you might not get this. Especially on a hot day, you might actually find that you've only got about 1 or 2 degrees to play with. So it might give you less than your rating. So that's also something to consider. If your temperatures are 100 degrees C like they are in the States, or 80, 100, 120 degrees C, you can then increase that. Your real-time rating systems actually come and can come into play a lot more benefit to you. So this is not generic, that's what I'm saying. It depends on your particular condition. Looking at the benefits, you allow more time for operators to make decisions, because now he doesn't have to shed load immediately as soon as he hits that rating. He can actually say, well, look, have I got time? Is the wind blowing? What's the story? You can defer capital expenditure. You can dispatch generation during capacity deficiencies. It also mitigates your reliability concerns. And you might get improved wind power utilization, so you don't get curtailment, and use a higher daytime capability. So really the real-time systems ensure the line won't contravene the statutory or annealing limits. But it doesn't allow, you say, well, real-time, we're going to run the line hotter. It might be running hotter than it would otherwise have run if you just use your static rating, but it won't run hotter than your design temperature. So if you don't have it really, you don't really know where you're sitting. So you might actually be running hotter than your design temperature at the moment anyway, but you most probably wouldn't be aware of it. So the real-time systems actually enable you to manage your load within that particular design criteria. So just in conclusion, I think looking around, the inverter-based resource penetration is going to continue to accelerate, whether you like it or not. The fact that the costs are coming down and it's free fuel, it just makes investment, it makes sense. A big thing, loads and generators are going to become interchangeable, mobile, and variable, and how you actually manage that. I think a lot of papers here at this conference have actually indicated there are systems and they're looking at ways of doing that. Your flow of power is going to be uncertain. And as I said, it's going to, where you thought power always went from transmission through to distribution, is going the other way now. And it goes away, it comes back in stochastic way, just where you don't want it or just when you don't need it. So it's really going to be uncertain. The other thing is that markets are going to continue to distort the power and the revenue flow. And the introduction of blockchain, well, we don't know how that's going to affect markets. So it's really going to, we've got not only technical aspects coming in with generation, and that you've now got man-made rules also playing a huge role in how your network behaves and operates. There's going to be requirements for more flexible and robust networks. So in other words, you're going to have to design networks that you don't have to run out and change everything all the time. So these could be smart networks where they automatically change settings. They can change voltage regulation and so on, depending on what's happening on the system at the time. And it's going to have to become more and more automated, because you just won't be able to plan and work out on everything from an operator point of view. So that's your flexibility and your robustness. The other big thing on flexibility is that now we're finding, in the past, CIGRE didn't really worry about, we had rotating machines and then we took it down to the meter, but we're now looking at how the boilers actually react to ramp rates, because that affects really the system. So the interaction between the generation and your type of generation fleet and what's happening on the network are now becoming a lot more critical. And we're actually setting up a work group to have a look at how boilers can be modified and what case studies are on. Some very good case studies in Poland where they've actually managed to change control systems fairly low cost to increase ramp rates and keep stability at really low loads. So this kind of thing's going to have to come through, because a lot of the coal you're just not going to get rid of overnight, and you don't really want to do that either. You're also going to need to have the ability to upgrade with a minimum additional cost. And that's really where you might find the use of the real-time systems and high-temperature conductors. But one thing that I'm finding is it's absolutely challenging and exciting going forward. You can now get involved in anything from blockchain designs right through to 10 gigawatt line design, which is absolutely amazing. So you have power engineers now, not what power engineers used to be. So I think it's a really great, a really great opportunity. And looking at CIGRE involvement, keep you abreast. We've got people from around the world looking at all of these all the time. And somewhere in the world, somebody's either working on a solution or they've found a solution. And if there isn't, there are a lot of people that know enough to get together as experts to find a solution. So thank you. Just some acknowledgements from the CIGRE Technical Council, and my company ESCOM, and the past president who helped me with a few of the slides. Thank you.
Thank you very much, Rob. That was very informative. There is a good time for questions, so can I invite questions from the floor?
There was a line going from like New Zealand to like South America or something like that. Who's like paying for that sort of stuff? Like where you have to pay more because it's mostly for us to use it, or like what's the deal with that sort of thing?
Basically, they are looking at the models. At the moment, they're looking at really just, can we even consider doing this stupid thing? I mean, it's you know, you look at this thing and you think, well, it's just absolutely not possible at all. And technically, they're now finding that it might actually be possible. And the Chinese have come up with different models where they can actually sell pretty much cheaper than what you can generate locally. So what they're saying is, we're going to sell you green energy. And they're not starting by taking it from New Zealand to America. They're looking really from China through Russia through to Europe. They're looking at the Korean Peninsula into China. They're looking through to Japan. So they're looking at that kind of thing to start with, and also from the Congo Basin, which has got about 80 to 100 gigawatt hydro run-of-river, which is renewable dream, to feed that through to Europe and to feed that down into parts of Africa in the south. So what they reckon is that because of the size and the amount of power they can transmit, and because it's free fuel, and they can give that to you at 24/7 because it's winds blowing somewhere and whatever. They reckon it's a good business case. They've done studies, but as I said, not on the. So they're looking now at 7 grids across north, south, and east, west. So that was just a concept drawing. The later ones are slightly more realistic and more practical. But I just put it up just to create some thinking.
Brian, please, a question rather than a viewpoint.
Well, congratulations. Very interesting paper. But it seems that your emperor of solar and wind power has got no clothes. The problem is that both solar and wind power only exist because they're subsidised. When the subsidies go, development stops. That's been well established. China is now abandoning subsidies for solar, and it's killed its industry. But all the money that you're talking about spending is only to overcome the problems of an industry which is imposed on us and is fundamentally uneconomic. Why aren't we pushing nuclear power, which is safer, cheaper, better, and doesn't have all these problems?
Yeah, look, the actual subsidies, in fact, with zero, the subsidy removal has not killed the industry. It's actually still going, and the prices are still coming down. So what happened was, especially in Germany, was the huge subsidies. But that's actually still coming down. So that hasn't killed the industry at all. The concept of the global grid is it will actually solve the problem, but the driver wasn't to solve inertia. You can solve it locally. You don't have to do that. You don't have to worry about having this global grid. The global grid was actually based on a zero emission business case, actually from State Grid, and it was concept was started in 2012. So it's not really to solve the problem. The motive wasn't the same. Now nuclear is actually still being considered, and in fact, what the problem on the big nuclear at the moment was the expense. And you can see not all of them are, you can't do there's a few things you can't do with like ramp rate and so on. But what they're looking at now is a small nuclear, which is actually one of a really good idea, because you get there's no emissions on nuclear, you've got a really good fuel. And if you're looking at places like Africa and so on, for the small 500 megawatt nuclear stations, which can be deployed fairly quickly compared to the 3,000 to 4,000 megawatt systems, that is definitely something to look at. And Japan, in fact, are looking at 500 megawatt nuclear now. So it definitely hasn't been, taken off the table as such. And what you need to do is actually get a good mix between the whole lot, and make sure that if your coal is going down, that you've actually got something to replace it. Because at the moment, the problem was in Germany, they stopped nuclear, put in renewables. The market actually pushed. That was an energy market, which is pretty useless for operations. So it'll give you all the renewables will now come in on an energy market, but you've got no ancillary services. So what they had to do was then burn the lignite, the brown coal, so the emissions went up. So as soon as you put in your renewables, that's actually not what you want. So you actually want to design your market, your network, and your fleet to ensure that you can get really the best low-cost, greenest combination. So nuclear definitely not off the table at this point.
Thank you, Rob. Okay, thank you for your questions. I'll bring this presentation to a close. I just want to kind of make a couple of remarks in relation to a vote of thanks.
Thank you.
Yeah, thank you very much, Rob. That was very informative. Rob's outlined for us kind of the 8 key challenges that CIGRE have identified, but particularly aspects around kind of increased customer participation and grid renewal, where he gave us some quite good insight in terms of the challenges around things like conductor selection and potentially how we may monitor things like conductor performance and loading in the future. It was very interesting, the kind of reference to the rural connection challenge. I think our speaker yesterday spoke about the fact, and I'd be corrected if my numbers are wrong, that to the future we might expect kind of up to 80% of kind of urban consumption, where we're probably sitting at about 50% now, I think was a US example. So I think that's a very interesting contrast in terms of the challenge compared to a global network, when you're also kind of considering how to overcome the kind of challenges around rural supply. It was, I think, important to note that we're back recognising the importance of transmission networks. It's not that long ago there was a lot of debate going on around the future of transmission lines. Ultimately, will they become redundant? But it's important to note, I think, that you've highlighted the importance of the transmission networks. Also, potentially how microgrids will operate from a standalone or an integrated perspective. We can't ignore either, I think you've highlighted to us. You also highlighted 10 areas of focus in relation to kind of things like active distribution and requirements around operational control. I think this is one of our significant challenges as we come to understand how our networks will be operated in the future. It was noted the reference to the wide range of brochures and information and resources available through CIGRE, so appreciate that. Again, it was really interesting to kind of just consider this balance between the big vision of global interconnectivity versus the practical challenges around giving good quality supply to rural community. And often we find these days that kind of rural communities have urban electrical supply kind of expectations. So I think you covered a lot of very good points, and we thoroughly enjoyed your presentation. So would you join me in thanking Rob for that presentation?